This is chapter 8, confidence intervals. In this course, we're actually not covering confidence intervals. We're going to skip forward to hypothesis testing. However, there are a couple of key concepts that need to be covered from this chapter. This is where you would find this stuff in your textbook. We're going to cover critical values. We're going to cover significance level. This is where we cover the t-distribution. So we're going to cover those things. It's in the confidence interval chapter, even though we're not actually covering confidence intervals. So first off, a point estimate is a single value used to approximate a parameter. Very important definition. Put an asterisk by that, put a star by it, highlight it, whatever you got to do. Make sure you know the definition of a point estimate. It's a single value used to approximate a parameter. And then we can elaborate on that and say, well, what are some examples of that? And the two most common, the two that you've seen before that we're going to start with and do our hypothesis testing when we get there, are going to be the following. First, we're going to say that the sample proportion p hat is the best point estimate of the population proportion p. And I have a note here just because depending on if you find different resources, sometimes they will report the population proportion as pi. Now, you can probably understand why we don't like doing that. That's because pi has a different meaning in math, right? It means 3.14, etc. And so, however, we like to use Greek letters for parameters. And so that's why some people use pi as the symbol for the population proportion, because the Greek letter for p is pi. However, just because pi has a different meaning, we will talk about the population proportion as p, the sample proportion p hat. We've seen both of these symbols before. Explicitly, we've seen sample proportion. We had those questions in the last chapter. What's the probability that the sample proportion of people boarding a plane exceeds 90% or whatever the question was? So we've used p hat. We've used p before, but in a slightly different context, but it's the same thing, right? Before we talked about p as the probability of success in a single binomial trial. And that's the same concept here. That would be the same idea. If you think about that, if we talked about flipping a coin 15 times, that's a binomial setup. Assuming the coin is fair, we would say that the probability of success in one of those trials is 0.5. Notice that's the same concept as a population proportion, because if I were to flip that coin an infinite number of times, 50% of the time it would land on heads and 50% it would land on tails. So it's the same thing, slightly different words potentially, but make sure you kind of align those in your head that when we talked about the probability of success in a binomial trial, on one of those trials, and then now the population proportion, we're using the same symbol because they are the same thing. And of course, the other one that we can talk about, you should be able to fill in the blanks from here. If I were to do another example, one we've talked about often, is we would say that the sample mean, x bar, is the best point estimate of the population mean, mu. So we are using this term point estimate, and again, it just means it's my best guess at what I think a parameter is. Okay, so again, very important term that we're going to use often in the rest of this course. Significance level is denoted as the Greek letter alpha, so another symbol to add to your list. In this section, we don't really dive into what significance level is. We're going to do that in chapter 9. So for now, what the actual definition of a significance level is, let's not stress about it. We'll just say that right now significance level and alpha are synonymous terms. And we'll come back to more of what that means shortly. We have to define a critical value. Critical value is the number that separates sample statistics that are likely to occur from those that are unlikely. And we notate that with an asterisk. So the idea is that we can have a critical value of any distribution. Right now, the only specific distribution we've covered is the z-distribution. Again, as I mentioned, we'll talk about the t shortly. But it's this idea that anytime we have any distribution with any specificity, we can always find critical values. And so we just add an asterisk on top of the letter of that distribution. It separates statistics that are likely to occur from those that are unlikely. And so if you've got a little fuzzy on what a critical value is, the idea is if I were to flip a coin 100 times, while I would expect to get 50 heads, I'm very aware that 50 is probably not going to happen. I'm probably going to end up with 51 or 52 or 49 or 47 or whatever it may be. And if you said, oh, no, sure, you can get 50 hits, okay, I'm with you. Let's take it a step further. If I were to flip a coin 1,000 times or 10,000 times or 100,000 times, let's even just go to a million. Let's say I flipped a coin. Let's say I was really, really bored. Flipped a coin 1 million times. Even though we expect to get 500,000 heads, like landing exactly on 500,000 seems pretty unlikely, right? It's possible, sure, but it's pretty unlikely. And so, how do you know what's likely to occur from unlikely? Let's go back to the simpler one that's easier to wrap our brains around, which is flipping a coin 100 times. If I get 52 heads, you would not really think anything is funny. You would say, okay, that's totally fine. Like, I expected 50, but I understand there's some random variability. I get 52, no worries. And if I got 82 heads, you would say that's unlikely. There's something's wrong with that coin. You're doing something with the way you're flipping it. There's something going on there. But what about 70 heads? Is that unlikely? And you might say, yeah, that's unlikely. And so what about 55? Is that unlikely? And you might say, no, it's not unlikely, but where do we draw the line? Right? 50, 57, is that unlikely? 59, 61, 63? Where exactly is that point that you start saying, I think there's something up with this coin? And the best part about this is just using this example, I think you can clearly see that if I were to force you to come up with a number that you deemed unlikely, and I was to do that for every single person in this class, there would be dozens of different numbers. There's no one easy way to come up with what's likely and what's unlikely in this scenario. So we have this idea of a critical value to come up with mathematically, how do we know what's likely versus what's unlikely? And that's a critical value. So anytime we think critical value, it's a cutoff. And so they should resemble what we did back previous in chapter 6 when we found cutoff values in the normal curve. Right? That's why we did that, was for this right here, was to say we can find cutoff values. Except before we were just finding random cutoffs, right? It was a third quartile, 95th percentile, or bottom 31% from top, whatever. It didn't matter because it was just arbitrary. We're going to find this cut point, but now we're going to find important cut points that say it's specifically values that are likely to occur from those that are unlikely to occur. And that's this concept of a critical value. And we can elaborate further. That's why they have this column. This definition isn't quite over with. The Z critical value, so Z asterisk, and I can subscript it with alpha over 2 here. We'll get to that in a second, is a Z critical value with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. So first off, it's more in the standard normal distribution. You knew that because I said Z. You knew it was a critical value because I put that asterisk there. And the subscript tells me what the area is in one of the tails. We're going to start off with everything being two-tailed. That's how we're going to focus in on this chapter. When we get to hypothesis test, as you're well aware, we can do one-tail test. We'll get to that later. Again, ignoring what significance level is, it's not really relevant today. The concept is if I have this significance level and I call it alpha, and I were to take a normal curve and I were to split that alpha in half, I put half of it in the right tail and half of it in the left tail, because the tails are what's unlikely, right? I want to make sure we're putting all the pieces together here. The tails are what's unlikely to happen. Okay, so it's this idea that, going back to flipping a coin 100 times, the tail cases of I got 80 heads or I got 20 heads, those are the things in the tails. That's what's unlikely. So if I were to take the significance level, whatever it is, alpha, again, alpha is going to have to be between 0 and 1 because the total area of the curve is 1, so it can't be bigger than that. And I were to say something that's unusual, something that's unlikely, are these extreme cases, and I have to consider the extreme cases on both sides. That's why I'm going to cut it in half. I'm basically going to go just find the cutoff that separates that alpha over 2 in the right tail and then the alpha over 2 in the left tail. And because the Z distribution is symmetric about 0, I only have to find the critical value one time, because this is the positive critical value and this one right here would be the negative critical value. And so, a little example, find the critical values for the following confidence levels. How we are going to work these problems is that we are going to say my confidence level is 1 minus alpha. Again, we're not going to do confidence levels really, so ignore that wording. We could just basically rewrite this as for the following significance levels, 3%, 5%, 10%. Okay, is the concept. So for this first one, I have a significance level of 3%. And again, we have to consider both sides, right? What if it's an extreme case to the large side? What if it's an extreme case to the small side? And when we get to these specific problems, that's going to be our default. Our default is we're going to have to consider both sides. What if you're off by a lot on the one side or off by a lot on the other side? If the problem specifically only wants you to consider one side, the problem will let you know. So right now we're going to go ahead and say we've got this 3% significance level, and I've got to consider what happens on the left and right. So I'm going to take that 3% and I'm going to cut it in half. You cut 3% in half, you get 1.5%. Now I'm going to work with it in decimal because when I go to my Z table or if I go to Excel, I have to work in decimal. So 3% cut in half to 1.5% converted to decimal is 0.015. And I'm just going to pull up my Z table and I'm going to say if I want to find a cutoff such that 0.015 is in the right tail, that means to the left is 1 minus that. 1 minus 0.015 is 0.985. And anytime I have the area to the left of a cutout, I go to my Z table, I find the closest value to that on the inside of the table, and I see what Z-score that leads me to. Notice you could have found the left critical value. If you see in your notes there, you have a little picture already drawn for you. You could have found the left critical value, and then didn't have to subtract from 1. You could have just looked up 0.015. Now notice that would have taken you to a negative. But again, we know that if we have a critical value cutting off the large extreme values and the small extreme values, I know I have to have a positive and a negative. And so in this case, the closest Z-score there would be plus or minus 2.17. Do the same thing for 95%. Again, 95% confidence, that just means 5% significance. And so cut that in half, work in decimal, that's 0.025. And the closest Z-score to that, again, if you found 0.025, you'd find the negative. If you subtracted that from 1 to get 0.975, you'd get the positive. You'd be looking at plus or minus 1.96. And then for the last one, if we have a significance level of 10%, we cut that in half, that's 5%. So in decimal, that's 0.05. Just be careful converting to decimals. You don't lose or add in an extra zero somewhere. If we look up the value closest to 0.05, it looks like it's right in between 1.64 and 1.65. Also, if you look at the bottom of your Z table, you have a little cheat sheet down there, and it actually tells you we can be a little more precise and call that 1.645. So that little table in the bottom is going to be really nice for you to find critical values for the most common significance levels. It does not give you the answer for all significance levels, just the most common ones. You need to be able to do both. You will see some questions in your homework, and you will see at least one question on each of your exams coming up that ask you to find a critical value for a non-common significance level. So use that little cheat sheet at the bottom. That's great, but also be able to find a critical value for something like a 3% significance level, like we did in that first example. That's an important skill that we already learned back in chapter 6. I want to make sure that you can still exercise those muscles. All right.